Hello, I'm Animesh Chatterjee, Scientific Associate at CERN. So first of all, I would like to thank the organizer for giving the opportunity to talk about the status and the results from the ICARUS experiment. So let's first try to understand why we need the ICARUS experiment at SBN, which started from the short-baseline anomaly. First, the LSND experiment, which tries to understand the neutron oscillations, looking at the muon antineutron oscillations to electron antineutron oscillations. However, they have observed an excess on the events, which meaning cannot be fitted with the three-flavor oscillation. Later, the mini-boon experiment at Fermilab tries to investigate more the results that LSND observed using the same L over E. They have taken data both for the neutrino and antineutrino run. For the neutrino run, they have seen an excess in the lower energy with a significance of 4.8 sigma. That doesn't fit with the standard three-flavor oscillation. To fit the data, both for the LSND and the mini-boon, we need to have a higher delta M square of the order of 1 eV square. However, not only by the LSND and the mini-boon, there are other experiments also observed same kind of anomalies, mostly in the shorter baseline. Started from the spectra looking at the reactor experiments for neutrino 4 experiment, for example, and some of the experiments looking at the solar neutrinos, and they have tested for the calibration purpose, they have used the radioactive source where they have seen this similar kind of excess, for example, the gallium experiment. So, however, there is an anomaly initially observed by looking at the flux calculated from the reactor spectra, which was now recalculated and well matches now within the expected. But if you combine from the reactor to the radioactive and from the accelerator experiment, mostly in the short baseline neutron oscillation experiments, the data cannot be fitted with the standard three-flavor oscillations. So can there is a common explanation of all of these anomalies? One of the most favorable one, which I'm going to talk about, the inclusion of a light sterile neutrino. However, there are other possibilities, including the dark sector model tries to understand excess from the dark matter particles, dark neutrinos, heavy neutral electrons, as well as other conventional explanation from the single photon production reactor flux model and so on, but other theoretical model as well, as I'm not able to share all of that. The recent combined analysis of a neutrino 4 galaxy SAGE and the best data clearly hints to a heavy a sterile neutrino of a mass square difference around 7.3 eV square. In looking at the sterile neutrino from the theoretical point of view, this also, so as it is a sterile, doesn't have any weak interactions, but can affect the oscillation through the mixings. It is a right-handed neutrinos by definition. So to generate a neutrino mass within the standard model, need to have a right-handed neutrino as well. So in a sense, both the theory and the experiments are motivating towards a sterile neutrinos. Now, to understand or discover these scenarios, the short-baseline neutrino program at Fermilab is designed using two detector concept, which is the FOR detector, which is ICARUS. I'm going to talk about that more in detail. And the near detector is BND. Both are the liquid argon TPC detector. The primary goal is definitely addressing the sterile neutrino anomaly that has been observed, as well as the neutrino argon cross section, which are huge statistics, and they reach beyond standard model physics program using the new beam at ICARUS, as well as using the booster neutrino beam at SBND. So ICARUS continues to operate for last 5 years. SBND started taking data in 2024. However, microboon ran from 2015 to 2021. Now, looking at the expected sensitivity from the experiment, including the SBND, ICARUS, and combining the microphone results, for 3 years of operations, it will be able to achieve a world-leading sensitivity, which will resolve the anomalies observed by the LSND with a significance of 5 sigma. The joint analysis of ICARUS and SBND data will explore the area relevant to the reactor and the gallium anomalies as well. Now, going quickly about which who are not familiar with the technology itself, that the SBN program is using the liquid argon TPC technology, where is basically when a neutrino or any charged particles enters and interacts within the liquid argon, produces the ionizations and the scintillation light. The ionization basically drift using the electric field and finally collected by the wires, and the scintillation lights are collected by the light collection systems, both for the ICARUS and the SBND detector. Now, the ICARUS is the first large-scale liquid argon TPC detector with two identical modules of T300, a total active mass of 476 tons. There are the drift distance of ICARUS is 1.5 meter. The drift time around 1 milliseconds. There are 3 signal wires, 2 induction and 1 collection plane. There are 360 PMTs which are collecting the light informations, which with a large number of around 54,000 of channel collecting the charge coming from the ionization. So in terms of the installation and operations, the detector installation started in 2018, completed in end of 2019. As you can see, the detector installed in pit, and then the top CRT installed, then 2.1, then after both the CRTs, completion of the CRT installations, 2.85 meter of concrete overburden installed in order to reduce the cosmic background, where you can clearly see from the plot that the cosmic background are reduced by a factor of 2. So the detector filled in April 2020, fully operational from August 2020. So in a sense, ICARUS completed 5 years of successful operation and continues to operate. This is the list of the data that taken by the ICARUS, both from the BNB as well as the NUMMI beam. For the NUMMI, it took both for the forward Hahn current, which is the neutrino run, and the reverse Hahn current, which is the anti-neutrino run. Currently, we are taking around 5 runs. So in terms of the performance of the detector, it started the physics data taking when the electron lifetime is greater than 3 milliseconds. However, the detector is performing very well with a electron lifetime greater than 6 milliseconds. And the trigger performance of the detector is greater than 90% with a thresholds of energy greater than 100 MeV. Here I'm showing the event display that from the data itself coming both on the BNB as well as from the NUMMI beam, clearly showing a mu CC candidate event where a proton track can be observed, proton and a muon event can be seen, as well as the EM shower candidate generated from the NUMMI data. Now, in terms of going before analyzing the data, the detector calibrations and performance were well understood by calibrating detectors with the cosmic muons and protons. So the calorimetry here, we are showing the plot of the calorimetry as well as the efficiency of the trigger, which is greater than 90%. For most of the greater than 200 MeV, but the thresholds is 100 MeV. So the trigger performance is really excellent. As well as for the first time, we have shown during the calibrations, the angular dependence of the recombination factor as a function of the angle between the track and the drift field. There are other lists. This is the list of the publications that came out from the calibrations and the performance of the detector system. Now, apart from the QPC, with the light collection system, we are also able to see the bunch structure of the beam very clearly, as you can see from the BNB, and we are able to see the resolutions of each bunch, which were very close to the intrinsic width that was expected from the BNB. Similar study performed for the NUMI as well. Now, going through the physics analysis and the mostly for the sterile neutrino oscillation measurement, the SBN program is searching for the sterile neutrino with the BNB, looking at the new mu disappearance and the new mu appearance channel, both for the ICARUS and the SBND. ICARUS detector will particularly have both the PNB beam as well as the new beam. So ICARUS, before the starting of the joint operations or joint analysis of the ICARUS and the SBND, ICARUS started focusing on the new mu disappearance channel, which is mostly focusing on 1 muon n proton 0 pion final state from the events in coincidence with the BNB for the ICARUS single detector oscillation measurement with two different reconstruction algorithms. The Pandora, the usual pattern recognition algorithm used by the previous liquid argon experiments, the microboom and others, and using the machine learning technique of spine to understand about the performance of the detector. Apart from the analysis, ICARUS also has developed a unique blinding strategy to ensure a robust and unbiased interpretations of the collected data. So, looking at the first analysis of the new mu disappearance channel coming from the BNB beam, the analysis performed with two almost independent pattern recognition, both for the Pandora and the spine. Both the frameworks developed a selection efficiency for the final state of 1 muon in proton events as a function of the neutron energy. Here you can see from the left plot the performance of the Pandora using different curves as a function of the neutron energy, and on the right showing the same performance for the spine, while the efficiency of the signal detection using the spine is around 80% and the purity around 92%, which is crucial for doing the final analysis of the sterile search using the new mu disappearance channel. Here showing the data Monte Carlo comparison with just 10% of the run-through data. Top plot showing for the Pandora as the bottom one for the spine for different low-level informations from the muon kinetic energy to the proton kinetic energy, as well as the angle between the muon and the proton. So there is an excellent agreement between all the variables, both for the Pandora and the spine analysis. So the new mu disappearance search has now completed, and the procedure for the signal unblinding. So stay tuned to see the final result soon. In terms of looking for the other physics signatures for the cross-section measurement, so ICARUS is located a 6-degree off-axis to the 120 GeV NUMI beam. This provides the high statistics for the neutrino argon cross-section measurement, mostly in the energy region, which is relevant for the Dune experiment, as this perfectly fits with the first oscillations maxima for the Dune experiment. The first analysis targets on the new MUCC 1 muon n proton 0 pion, which is enhanced in the quasi-elastic and 2p2h interactions. So here we are showing the cross-section measurement as a function of transverse kinematic imbalance, the delta pt, the transverse momentum imbalance, and the delta alpha t, the angular imbalance of the final state. Then this results is compared with the default Gini generator, which is a common framework here, common cross-section generator for SBN and the Dune. So the key significance of this analysis is the filling the gap at the higher energies for 1 muon n proton 0 pion final state on argon, which filling the crucial gap, and this will be useful for the future Dune experiment. The paper is under preparation, so stay tuned to see the final the paper. Now, looking at the other physics model, physics motivations for the sterile neutrino search. So ICARUS can probe the beyond standard model signatures using the NUMI beam, as the NUMI beam is off axis, in a sense, reducing the neutrino background. So the first BSM analysis involved the kaon decay and looking at the dimuon final state. Mostly looking at a scalar dark sector particles decaying into dimuon final state, as well as a heavy QCD axions decaying to dimuon state. So the productions can happen from both from the target as well as from the observer, mostly coming from the meson decay. Here, clearly showing the two final state dimuon signal at the detector. No, so the analysis performed by looking at any bump over the expected background at a specific value of the diurnal invariant mass. So the analysis performed both with the run one and run two data, run two NUMI data. There is no excess of events observed from the background expectation. However, if we look at the region of the invariant mass of dimuon from 0.24 to 0.31 GeV, there is a excess of around 0.19 sigma observed. However, this is within the uncertainties of the expectation. Then we've shown the exclusion limit both for the heavy QC reaction as well as the Higgs boson scalar. So ICARUS is able to produce the world leading constraints on the decay constraint of the heavy QC reaction. Mostly, if you look at the mass region greater than 260 MeV, as well as the stringent constraints on the mixing of the Higgs boson scalar as a function of the mixing as well as the mass of the Higgs boson scalar, which is recently published in PRL. Now, to conclude, the ICARUS experiment is currently operating at Fermilab as part of the SBN program for last 5 years, and it's continued to take data with a remarkable stability and performance of all the detector components. The ICARUS can take the advantage of both the BNB as well as the BNB, which is the on-axis, as well as the NUMI off-axis beam. Several analyses already completed. For the new mu disappearance with the BNB beam, looking at the 1 muon n proton analysis completed, and the results will be announced very soon, as well as new mu cross sections with the new mu. This is the first cross section measurement using 1 muon n proton 0 final state has been recently completed, and a wine and cheese talk given at Fermilab. Also, we have performed the first beyond standard model search using the NUMI beam by looking at the dimuon final state from the decay of a dark sector scalar. This is also there is a wine and cheese talk given, and we are the joint analysis of the ICARUS and SBND data with SBND data will start soon. So stay tuned for more exciting results coming soon from ICARUS. And as we have completed 5 years of operations, you can see the video for the operations of the ICARUS for last 5 years. So thank you.